Okay, well, it's been a long time since I've recorded a video, so hopefully this comes off clearly. Anyway, today we're talking about word problems, kind of how to apply this solving triangle business to real life problems. And again, I'll just stress, these are really, really important for any of you going into engineering world. These type of problems come up an awful lot. So, the essential question, yeah, what I just talked about. How do I use the trig properties to solve the real world problems if they involve right triangles? So first of all, I need to talk to you about some vocab. Oftentimes in problems we'll see these two different words. Depending on the sort of problem, you'll either see angle of elevation or you'll see angle of depression. Now, these angles are always coming off a horizontal line. So let's say I have this horizontal line. Maybe it's the ground, maybe I'm standing on it, maybe it's the, I don't know, the part of the ocean that's at the top, and so there are fish below it. This is supposed to be a fish. Anyway, the point is these angles always come off a horizontal line. So the angle of elevation is going up like this. Maybe we'll call it theta. So here's an angle of elevation. The angle of depression is going down. We'll call this angle alpha or something. So do you see how both angles, the elevation angle or the depression angle, are coming off the horizontal line? Not a vertical line, a horizontal line. Important for problems. Okay, so let's take a look at the first example. A fireman. You know what a fireman is, right? A guy that fights fires. He's trying to save a child in a burning building. Oh no, the child is in a window 10 feet off the ground. The fireman places his ladder at an angle of elevation of 70 degrees, and he has one of these cool extending type ladders. So how long must he extend his ladder to reach the window? Now, it's very important in these trig type problems that you draw a picture. There's like no feasible way of doing these just in your head. So first step, always very important, draw the picture and label everything you know about this picture. So first of all, we have a building. Here's the building. Maybe I'm standing on top looking out over this. Just kidding, I'm not in this problem at all. What is in this problem is the window that a small little child is in, and the house is on fire and the child needs to be rescued. So the house is burning, the child needs to be rescued. Now I know that the child is 10 feet off the ground. So let's draw the ground and let's label this is 10 feet from here to the ground. Okay, so 10 feet. Now the fireman, he is putting his ladder at an angle of elevation of 70 degrees. So here's his ladder. It's leaning up against the wall, and we're told that the angle of elevation is 70 degrees. So let's think about the angles that I have right here. First of all, buildings, especially if you live in Morocco, because they really like their rectangular buildings, they're always at right angles to the ground. So there's a right angle. But where is this 70 degrees? That's what I need to think about. What's the angle of elevation? And remember, I said the angle of elevation always comes off a horizontal line. So here's the angle of elevation, this 70 degrees. And it's asking how long must he extend his ladder. Well, here's his ladder. So I need to figure out how long this ladder has to be to reach the window. So there's my x. So let's take a look at the right triangle we have right now. We know that the one side is 10. We know what my angle is, and I'm trying to find, well, it looks to be the hypotenuse. So looking at that right angle, the second step in these problems is typically you'll have enough known quantities to do that thing where you pick the trig identity and set up an equation and solve. So in this case, I'm thinking, all right, orienting to this angle, what's the trig identity that deals with the opposite side and the hypotenuse? And that trig identity would be sine. So in this problem, sine of 70 degrees is going to be the right ratio to kind of encapsulate the known quantity and the unknown quantity. Since sine is opposite over hypotenuse, in this case, I'm going to do 10 over x. And I can begin to solve. The first step that would be really good to do here would be to multiply x on both sides. Because if x is on the bottom of the fraction, I'm not able to solve for it. So if I multiply both sides by x, cancels here, and I'm left with an x now that's on the top. Now the next thing I also need to do, and this is kind of like cross multiplication, is I need to divide by whatever sine of 70 is. So I'm going to divide both sides by sine of 70. Now my equation is x equals 10 over sine of 70. Because remember, sine of 70 is just a number, right? I can stick this into my calculator, and because all right triangles with 70-degree angles are the same, sine the calculator will be able to find. Like, it will know sine of 70. So all I need to do is stick this into my calculator, make sure that you are in degree mode, and if you don't know how to get degree mode, maybe ask a friend. I'm not going to show you in this video. All I need to do is go 10 divided by sine of 70, and I get 10.64, and we'll just cut it off there. We'll round to the nearest tenth. This would be in terms of feet. So my ladder apparently is 10.64 feet. Now we can ask ourselves if this is a reasonable quantity. Remember, the hypotenuse always needs to be the longest side, and in this case, yeah, this is longer than the opposite side of 10. So it seems like this is a reasonable quantity. All right, let's just take a look at one more example. A plane is currently at an altitude of 20,000 feet and is beginning its descent to the runway. So if you've ever flown before, usually you know that about 30 minutes or so before you land, your plane is really high, and the pilot will come on and say, hey, we're beginning our descent. And that means the plane is angling down and it's starting to descend so that it can hit the runway. And we know that the angle of depression is 5 degrees. I want to know how far along the ground is the plane from the runway. Okay, so first of all, this picture is a little more complicated. I'm going to start off by drawing an excellent plane. There it is. It's perfect. Oh, it needs a little tail. I always fly Ryanair, so I'll officially endorse Ryanair here, and hopefully they'll watch this video and give me some ad money. This plane is flying along, but it's not anymore. It's beginning its descent. And remember, the angle of depression we said is always off the horizontal. So even though the plane is supposed to be flying horizontally, it has begun its angle of descent. So this right here is my 5-degree angle. Now, many times when I see people do this problem, they'll just draw a right triangle and they'll just be like, hey, 5 degrees because I know I need a right triangle. Don't do that. Actually draw your picture and think about what is the angle of descent. Remember, I said the angle of descent is always off of a horizontal line. So let's label some other known things. First of all, here's the runway that the plane is trying to hit. I also know that it is at an altitude of 20,000 feet. That means it's off the ground straight up 20,000 feet high. And I'm trying to find how far along the ground. So here's my right angle because the plane is 20,000 feet high. How far along the ground is what I'm solving for. And I do have an angle, but the issue is this angle, it's not actually in my right triangle, is it? Like, here's my right triangle. I either need to know this angle or I need to know this angle. And right now, the angle that they gave me is outside of that. So I can do one of two things. First, I can notice that this angle is complementary to the 5-degree angle that I'm given, which would thus indicate that this is 85 degrees. See how this makes a right angle? So these two angles need to add up to 90. That would make this an 85-degree angle. The other thing that I could do is notice that since this is a horizontal line and the ground is also a horizontal line, these lines are parallel, and if you notice, this and this are alternate interior angles. Remember that from geometry? So since that's a 5-degree angle, this is also a 5-degree angle. So at this point, I now have some angles inside my right triangle. I can use either the 85-degree angle or the 5-degree angle. It really doesn't matter. Let's use the 85-degree angle, just because I feel like it. And orienting to the 85-degree angle, what encapsulates the opposite and the adjacent? I know that that is tangent. So tangent of 85 degrees is going to equal x over 20,000. Whoa, I don't know what I'm drawing here. X over 20,000. Notice that if I had chosen tan of 5 degrees, if I had oriented to this angle, the opposite and adjacent would have switched, and I would have been doing 20,000 over x. Either of these are perfectly valid. This one's going to be slightly easier to solve because I don't need to take that initial first step of multiplying by x that I did here. Instead, if I use the 85-degree angle, all I have to do is multiply both sides by 20,000. And so x is going to equal whatever 20,000 times tan of 85 degrees is. And again, this is something that I can stick right into my calculator because all 85-degree right triangles are exactly the same. And I get that I have 228,601. Let's do 0.05. And I think I'm working in feet here. And this seems like a plausible number because look how drastic this angle is. Since this angle is so drastic, really my right triangle looks something like this. This 85-degree angle is a really wide one, and so this side should be way longer than this side, which my answer is. So this is a plausible answer. All right, so summary. You need to draw the picture. That's always step number one. Identify all the unknown data, and then simply pick the correct trig identity and solve. Have a nice day.